So now we are ready to start doing our examples for area between curves. And the thing about doing an area between curves, what is going to be the most difficult part is when you're writing your integral, you've got to figure out what your limits of integration are. Like, what are you trying to find the area between from A to B? Because sometimes they tell you, sometimes they don't. So like in this first example, they don't tell us. So we've got to figure out our A and B. So sometimes that's the most important, most complicated part of the whole problem. And so sketching it becomes really important. So knowing what these graphs look like and sketching a picture of it is the most challenging part. So this first function is 2 minus x squared. So first thing I want to do is draw a picture of what that looks like. So 2 minus x squared, I can do this without a calculator, but if you've got a calculator, you can type this in y1, type this one in y2, and then just graph them, and then you can also calculate the intersection on the graphing calculator. But this one's an easy enough one to do. I don't need a calculator for. 2 minus x squared. 2 minus x squared is going to be the parabola turned upside down and then up 2 units. So that's going to look like this. Up 2 units. So it's a parabola, a smile turned into a frown, and then shifted up 2 units. Okay? So that's what that one looks like. Now the graph of g of x equals x, that's just the line y equals x. So that's the diagonal that goes through the first and third quadrants. So this function is the 2 minus x squared. And then my line is the x, the y equals x line. So this is y equals 2 minus x squared, and this is the line y equals x. I want the area between these two. All right, so I want that little half a heart there. Okay, so I'm going to do the integral. I'm going to do top curve minus bottom curve. Remember, the area from A to B, it's f of x minus g of x, which is the top curve minus the bottom curve. That's what we're going to do. So our top curve is the 2 minus x squared, and then you're going to subtract the bottom curve, which is the x, and then put our bookend dx. So the only thing we need is what are our limits of integration. So we are trying to find the area between this intersection point and this intersection point. So I've just got to figure out what those numbers are on the x-axis. What are my x coordinates of those two intersection points? That's my A and my B. So I'm integrating from A to B, my x coordinates of these points. Now, like I said, you can put these in y1 and y2 and graph them on the graphing calculator and figure out your intersection by doing second trace, which is calc, and doing number 5 and find an intersection. Or I can just set these equal. These are easy enough that if I just set these two equal to each other and solve, I can move everything over. So that'll be positive x squared plus x minus 2. And then you could just factor it. This factor's real easy into 2 and 1. And we want more positive in the middle, so that'd be a positive 2 and a minus 1, and that would also give me the negative 2. So my two answers here that makes this 0 would be negative 2 and positive 1, which are exactly my x coordinates over here, negative 2 and positive 1. Those are my intersection points where those two graphs intersect. That's my x coordinates. So we're going to integrate from negative 2 to positive 1. All right, so now we can do this by hand. All right. So my antiderivative is going to be 2x minus the antiderivative of x squared is x cubed over 3 minus the antiderivative of x is x squared over 2. I don't need the plus c because I'm evaluating from negative 2 to 1. So this is where we do the fundamental theorem of calculus, right? So I'll plug 1 in first. So when I put 1 in, it's going to be 2 minus putting a 1 in is 1/3. Minus putting a 1 in is going to be 1/2. Now putting negative 2 in here, I'm going to have negative 4. Putting a negative 2 in here is going to be negative 8/3, but I'm subtracting negative 8/3, so that'd be positive 8/3. And then putting a negative 2 in here is going to make 4, but it's going to be minus 4/2, which makes it minus 2. So now if I work out my math here, I'm going to just distribute the negative sign. So this will be 2 minus a third minus a half. This will be plus 4. This will be minus 8/3. And then this would be plus 2. So when I look at combining these together, the negative 1/3 and the negative 8/3 makes negative 9/3. So that makes negative 3. And then I have 2 and 4, and 2 makes 8. So 2 plus 4 plus 2 is 8. And then I've got minus a half. So I've really got 8 minus 3.5. So 8 minus 3.5 is going to be 4.5. All right, so that answer is going to be 4.5. So if you remember from last year, we did something called Math 9. So you could type this into Math 9, and if you do, it will tell you the answer 4.5. All right, but we should be able to do these by hand without a calculator. All right, so you can Math 9 all of them just to check yourself, but you should be doing them by hand to make sure that you know how to do all of the calculus work. All right, but use that calculator to check your work and check yourself. Make sure you're monitoring yourself, that you know what you're doing. All right, so this next one says, find the area of the region bounded by the graphs of this function, that function, 0 and 1. All right, so let's sketch a picture of what this looks like. So I've got x squared plus 2. Well, that's just x squared, which is a smile. All right, and I'm adding 2 to it. So I'm going to look like this, where this has been shifted up to 2. So that's x squared added 2. Then I've got y equals negative x. Well, y equals negative x is this negative diagonal. So there's y equals negative x. And then I have x equals 0. That's actually the y-axis. All right, so that's my y-axis here at 0. And then x equals 1 is a vertical line at 1. So then I've got a vertical line here at 1. So I want the area enclosed by all 4 of those things. So enclosed by the parabola, the diagonal line, the y-axis, and then this vertical line at x equals 1. So I want this area in here. All of this little area right here. All right, so I know it's going to be an integral, and I already know the numbers here because it's already on here for me. So I'm going to go from 0 to 1 because I'm going from this vertical line to this vertical line. So 0 to 1. And I'm just going to do top curve minus bottom curve. So pretty straightforward. So my top curve up here is the parabola. So x squared plus 2 minus the bottom curve. And my bottom curve is the negative x. And then I put my bookend dx on there. Alrighty, so there's my problem. I'm going to go ahead and simplify it here. That's going to be x squared plus 2 plus x. Alrighty, so now we do the antiderivative. So x cubed over 3 plus 2x plus x squared over 2. I don't need the plus c. I'm going to evaluate from 0 to 1. So now I'm going to do the fundamental theorem of calculus. All right, so I'm going to put a 1 in. So that's going to be a 1/3 plus 2 plus, I'm putting 1 in, 1/2. Minus, now I'll put a 0 in, and when I put a 0 in all those, I get a big fat goose egg. So my answer is really 1/3 plus 2 plus 1/2. So if I wanted to add all this together, that's going to be 2/6 plus 3/6. So the answer is 2 5/6. So if you're math 9ing it, remember you can always do math 9. Math 9 is probably going to tell you 2.8333 repeating, because I think that's what 5/6 is. All right. So that way you can double check your answer. Remember, don't do it all with math 9. Go through and do the work yourself, and then check your answer with math 9 by just putting this integral in to the calculator, and it'll tell you the answer. All right, check your work. All right, the next one says, find the area of one of the regions bounded by these two curves. All right, so let's sketch out what this would look like. Well, we know sine looks like this, right? And it keeps on going this way. And then cosine starts above and comes down, right? Like this. And then up. All right, so that's the cosine curve, right? So we want the area of one of the regions bounded by these curves. All right, so we want one of these regions. All right, this curve here is the sine, and this curve here is your cosine. So I already know I'm going to be doing top curve minus bottom curve. So I'm going to be doing sine minus cosine. So now I've just got to figure out what are my limits of integration. So where do these two guys intersect each other? Okay, so you can put these in y1 and y2, and you can do the second trace in calc number 5 and figure out their intersections that way. Or we can set them equal. Just think about this on your unit circle. Where does sine equal the cosine on the unit circle? So remember, the sine is the y-coordinate on the unit circle, and the cosine is the x-coordinate on the unit circle. So where on the unit circle does your y-coordinate and your x-coordinate equal each other the same, right? So where on the unit circle are the two coordinates exactly the same? Well, that's pi over 4. Because at pi over 4, they're both radical 2 over 2 and radical 2 over 2. And then the other answer is at 5 pi over 4. So at 5 pi over 4, that's where they're both negative radical 2 over 2 and negative radical 2 over 2. All right? So that's your two answers. You're looking at pi over 4 and 5 pi over 4. Okay? So I know I'm going to integrate from pi over 4 to 5 pi over 4. So now we're ready to do our antiderivative. So the antiderivative of sine is negative cosine minus, and the antiderivative of cosine is sine. And then I don't need my plus c because I'm evaluating from pi over 4 to 5 pi over 4. Okay? All right, so now we do the fundamental theorem of calculus, right? So now we're going to put 5 pi over 4 in here, so that'll be negative cosine 5 pi over 4 minus the sine of 5 pi over 4. All right, then we're going to subtract and we're going to put pi over 4 in there. So this will be negative cosine of pi over 4 minus the sine of pi over 4. Now, you cannot leave it like this. You have to actually go find the answers. All right, so we need to figure out what is the cosine of 5 pi over 4. Well, we know that's negative radical 2 over 2. Minus, and then what is the sine of 5 pi over 4? Well, I know that's negative radical 2 over 2. Minus, parentheses, negative. All right, what is the cosine of pi over 4? Well, that's radical 2 over 2. Minus, what is the sine of pi over 4? That's radical 2 over 2. Okay, so now I'm just going to do my math here. So I've got, yeah, and that was a little negative right there. So I've got minus a negative, so that's going to be radical 2 over 2. Then here we got minus a negative, so that's also going to be plus a radical 2 over 2. Then over here I'm distributing the negative across, so that's going to be adding radical 2 over 2. And then distributing that negative, I'm also going to be adding a radical 2 over 2. So really, what have I got here? I've got 4 radical 2's over 2, which the answer is 2 radical 2. All right, so the answer is 2 radical 2. And then if you math 9 it, you're probably going to get 2.828, I believe the decimal is. I believe that's what it is. because the square root of 2 is 1.414. So if you double that, that'll be 2.828. So you can math 9 it, but then just be sure you double check your answer, because we can leave this as 2 radical 2. We don't need to simplify it to a decimal or anything. But you can always double check your answers by math 9. All right, this one. This might be the most complicated one that I do. All right, and the reason is because of what the graph looks like. Now, this is one where I really don't want to do this by factoring all this. I mean, it could be done by factoring both of these and then graphing it. These are probably one where you want to put it in Y1 and Y2 and graph. And the reason is because when you do that, you get a much more interesting picture. All right, so here's what our picture ends up looking like. We've got a parabola. So here's our parabola. And then we also have a cubic function. All righty, and my cubic function, I'm going to draw it like this. All right, there's our cubic function. So notice this function is the cubic one. So this function, 1, 2, 3. So this function is the 3x cubed minus the x squared minus the 10x. And then, of course, my parabola here, my parabolic one, this one is the negative x squared plus 2x. So putting that in the graphing calculator makes it a whole lot easier to see it. Okay, now the other reason you need to put it in the graphing calculator is because you notice when you graph it, and you may not be able to see all of this in one window, you got to be mindful that these two guys intersect each other in 3 places. So there are 2 areas in which I need to find the sum total of the area of these 2 combined regions. All right, so I need the intersection point here. I need the intersection point here, which I'm assuming is fairly easy to figure out. And then we need the intersection point right there. So this is where you need to go to second trace, calc, number 5, figure out your intersections. So this point here is the point -2, -8. So this is -2. So this point is -2, -8. So that means my x value is -2. This is actually the origin. So that is nice. That's the origin 0, 0 there. And this point here when they intersect is the point 2, 0. So this is 2. So in order to find all of this combined area, there's a couple things I can do. So I'm going to show you the one way first. You're going to do 2 separate integrals. You're going to do the integral from -2 to 0. All right. And you're going to do top curve minus bottom curve. So from -2 to 0, the top curve is the cubic function. So that's going to be the 3x cubed minus x squared minus 10x. So I'm going to take that function and I'm going to subtract the bottom curve, which in this case, the bottom curve is the parabola. So I'm going to subtract negative x squared plus 2x. And I have to make sure that I put that in parentheses because I'm subtracting that whole quantity. All right, so I'm doing -2 to 0 of 3x cubed, and then I've got a minus x squared, and then this is going to be minus a negative x squared, so that's going to be adding an x squared, so those guys are going to cancel. And then I've got minus 10x minus a 2x, so that's going to be minus 12x's, because I've got -10x minus this 2x, so I'm going to have minus 12x's. So that's what it simplifies to be. All right, so I need to find that answer first, all right, or partial. Then I'm also going to have to do the integral from 0 to 2. All right, so let's go ahead and do this one first. So I'm going to do the antiderivative, so that'd be 3x to the 4th divided by 4. Hello. All right, 3x to the 4th divided by 4. Minus 12, this will be x squared divided by 2. I don't need the plus c because I'm evaluating from -2 to 0. Okay? All right, so I'm going to do the fundamental theorem of calculus. So that's I'm going to put 0 in first, which ends up being a big fat goose egg. And then I'm going to put -2 in here. So -2 in there, -2 to the 4th power is 16. 16 divided by 4 is 4. And then 4 times 3 is 12. All right, then it's minus 12 over 2 is 6, times -2 squared would be 4. So I'm going to end up having 12 minus 24, which is -12, and then subtracting 0 minus -12 is going to give me an answer of 12. So that means the area of this left piece is 12, okay? Now I need to do the area of the right piece. So now I'm going to do the integral from 0 to 2, and now we have to do top curve, which this time the top curve is the parabola. So that'll be -x squared plus 2x minus the bottom curve. So now the bottom curve this time is the cubic function. So putting that in parentheses will be 3x cubed minus x squared minus 10x. And then I put my book in the dx. All right. So now let's see what we end up with this time. So we're going to have, I'm going to start with the first one. That'll be -3x cubed. And then from x squareds, I'm going to have -x squared, and this will be minus -x squared, which makes it plus. So those cancel. And then I'm going to have a 2x minus -10x, which will be adding 10x, so that'll be plus 12x. Okay? And then I got my bookend dx. And that should be the same thing as this up here. Yeah, it is. It's just negative sign because I subtracted the other direction. All right, so now we're going to do our antiderivatives. So our antiderivatives are going to be -3x to the 4th divided by 4 plus 12x squared divided by 2. I don't need my plus c because I'm evaluating from 0 to 2. So now I do my fundamental theorem of calculus. So I put a 2 in first. So putting a 2 in here will be 16 divided by 4 is 4 times -3 is -12. Putting a 2 in here, 2 squared is 4. 4 times 12 is 48 divided by 2 is 24. So plus 24. Then I put 0 in here and it gives me a big fat goose egg. So then I've got -12 plus 24, which is 12, minus 0 is 12. So that means the area of this second piece is 12. And that's poinky dink that they both end up being an area 12. That's pretty cool. All right, that doesn't always happen. So the area on the left is 12, the area on the right is 12. So that means the area, combined area of these two pieces is 24. All right, so if you were actually writing this answer out on a test, you probably would write it as the integral from -2 to 0. And here's the short way I could do it. I know that the cubic function is function f, so I could say that that's f of x minus g of x dx. And then I'm going to add to that the integral from 0, was it 0 to 2? Yeah, it was. All right, then it's going to be 0 to 2, and I'm going to do now g of x minus f of x dx. So I could write that on the AP exam. I could actually use the expressions that they gave me in the problem, the f of x and the g of x expressions that they gave me up here in the problem. I could actually use these in writing out my integrals, especially if it was a calculator active problem. And then I could actually just type it in the calculator and that would give me 24. All right, because this ended up being 12, this ended up being 12. And so when you add it together, you got 24. Now, there is a little shortcut I want to share with you that you can do for this. All right. Notice what the difference was between these two pieces. The only difference was which curve was on the top and which one was on the bottom on each piece. So on this first left piece, the cubic was on the top and the quadratic was on the bottom. And on this right piece, the quadratic was on the top and the cubic was on the bottom. And we were doing -2 to 0 for one of them, and we were doing 0 to 2 for the other one. All right. Now, there is a quick way that you can do this, and it saves you some time, but it can only be done with the calculator. So if this is a calculator active question, this is what you would want to do. I would want to do all the way from -2 to 2. I'd want to go all the way from -2 to 2. And I would want to use absolute value bars, because absolute value bars makes it to where it doesn't matter which curve I put first. So then I could do f of x minus g of x and put that in absolute value bars, so that when it does the difference, top curve minus bottom curve, it doesn't matter which curve is on the top. And so it's going to do the absolute value, so I will keep getting a positive answer. And it's going to find the total area all the way from the -2 all the way over to 2. And then this answer should give you 24, or will give you 24 when you put it in the calculator this way. All right. So that's the little trick, and that only works though if you're allowed to use a calculator. So if this was a non-calculator question, obviously you can't put in absolute value bar. I mean, you can only do the absolute value bars when you're using a calculator, because you can only do antiderivatives of these expressions. You can't do the absolute value ones. So if it was a calculator question, we're in business. If it's a non-calculator question, then you have to do each integral individually and then sum up your two answers. All right. So that just gives you a little bit on that one. So what made that one hard was because it intersected they intersected 3 times, so it gave you 2 areas. Okay. Now, this is our last one here, and I wanted to give this one that was turned sideways. All right. It says find the area of the region between these two. Now notice it says f of y equals 3 minus y squared, and g of y equals y plus 1. So these graphs are turned sideways. All right. So 3 minus y squared. So you just have, you know what a y squared looks like. It's a parabola. So instead of being a vertical parabola, it's a sideways parabola. So if you have positive y squared, it goes this way, right? If it's a negative y squared, if it's a negative y squared, then the graph is turned this way with the mouth open on the left, okay? So this is positive y squared, and this is negative y squared. Of course, they would be touching the origin if it was just y squareds, all right? So I have y squared, and I have it negative, so that means it's the one that's opening to the left. And then I'm adding 3 to it, so that scoots it over 3 to the right, okay? So that makes that graph look like this. All right. So there's a sideways parabola opening on the left side, and then move 3 to the, so there's 3 to the right. So there's what that looks like. All right. Now this is an equation of a line. Okay. Now the easiest way to think of this is to think of this as x equals y plus 1. So if you reverse that in your brain, then you're going to have move this 1 over the other side. So it's really the equation of y equals x minus 1, right? So this is x equals y plus 1. And so if you just move the 1 over, then you got x minus 1. So it's the equation that starts at -1, okay? Now, the thing is, we got to know, where is -1? Is this -1? Is -1 up here, or is -1 down here? So think about, where would this equal 0? If x were 0, y would have to be the square root of 3, which is 1.7. So I know this intersects right here at 1.7, negative and positive. So that means -1 is going to be inside here. So -1 is going to be in there. And then it has a y-intercept of -1 and a slope of 1. So we're talking about a diagonal line that looks like this. All right. So there's what that looks like. So we're wanting the area of this little crescent moon between them. So that's the hardest part about thinking about sideways graphs that turn sideways. You got to have to know what they look like. Okay. Now, I need to find their intersection points, because I know I'm going to integrate top curve minus bottom curve, except I'm turned sideways. Okay. We're turned sideways, so instead of doing top curve minus bottom curve, we're going to do right minus left. Okay. All right, so we're going to do right minus the left. So instead of doing top minus bottom, because we're in y values, we're going to do the right curve minus the left curve. So if you notice, the curve that's on the right side is the parabola. So we're going to do 3 minus y squared minus the curve on the left, which the curve on the left side of this shaded area is the line. All right, so my line, I'm going to subtract y plus 1. Notice we're in terms of y, so I'm a dy, okay? Which also means I have to have y coordinates on my integral sign. So I can't go from x value to x value. I have to go from y coordinate to y coordinate, okay? We have to go from y coordinate to y coordinate. We're still going to do this the same way, though. We're going to find out where these are equal, okay? So we're just going to set these equal and solve. So 3 minus y squared equals y plus 1. I'm just setting them equal to figure out their intersection points. All right, so I'm going to move everything over here. So that'll give me y squared plus a y. And when I minus the 3 over here, that'll give me a minus 2. So now I'll just factor it. So y and y, 2 and 1, looks the same as what we had earlier, more plus than minus. So my two solutions are -2 and +1. So -2, +1. So that means down here, the y coordinate is -2, and up here, the y coordinate is 1. We already know the x coordinate is just less than 3. All right, but my y coordinate is 1. All right, so now I'm going to integrate from -2 to +1, and I'm integrating right curve minus left curve. So whenever it's turned sideways, you do right minus left. All right, so right curve minus left curve. Instead of doing top minus bottom, we're sideways, so we do right minus left. You're always in terms of y's when you do right minus left, when you're sideways. And so you always have to make sure you have y values on your integral sign. Okay? So I'm integrating from -2 to 1. And I'm just going to put this out, simplify this a little bit before I do the antiderivative here. So that's a -y squared. I'm going to have a -y. And this will be 3 minus 1, which will be 2. All right, so now I'm going to do the antiderivative. So that'll be -y cubed over 3 minus, the antiderivative is y squared over 2 plus 2y. I don't need my plus c because I'm evaluating from -2 to 1. So now I'm going to do the fundamental theorem of calculus. So I'm going to put a 1 in first. So if you put a 1 in here, that's going to give you a -1/3. Putting a 1 in here will be a -1/2. Putting a 1 in here will give me a 2. Then we're going to subtract. We're going to put -2 in here. So if I put a -2 in here, that'll be -8, but then it's negative, so it'll be +8/3. Putting a -2 in here will make 4. And 4 over 2 is 2, and then minus, so -2. And then putting a -2 in here will make -4. So let's see what we got. We got -1/3, -1/2, +2. Distributing this will give me -8/3. That'll be a +2, and that'll be a +4. So let's see here. -1/3 and -8/3 is going to be -9/3, which gives me -3. So I've combined those. And then 2, 2, and 4. This is looking very familiar. 2, 2, and 4 is 8. All right, so 2 plus 2 plus 4 is 8. Then minus a half. So this is giving me 8 minus 3.5, which is going to give me 4.5, which I believe is an answer to a question we had earlier. All right, so the calculus, the algebra part turned out to be very, very, very similar. So that means the area between these two curves is 4.5. All right, so there you are. So that's turning it sideways. So you can do sideways as long as you remember you're going to be, everything is in y's. And so most students forget to put the y coordinates on the integral. They still keep the x coordinates. So you just have to remember when your functions are in terms of y's, then you got a dy on the end. So that means your limits of integration on either side are also going to be y values. And yep, that was the last one. So now you've got a few problems to practice on your own.